It's wonderful to see so many people back again today. It's my great pleasure to be introducing Professor Michael Plum this morning. He's going to talk about computer-assisted existence and multiplicity proofs for semilinear elliptic problems, unbounded and unbounded domains. So Michael, it's all yours.
So thank you very much, Jay, for the introduction, and thank you to all the three G's, the J's, so JP, J, and JB, for the invitation to talk here. I must apologize. Some of you may have heard this talk in another version already, but I think also for those who had heard it already, I will add new information today. So, this geht das nicht. So wait, hang on. So now this moving the screen doesn't work. So okay, so I will be talking about elliptic boundary value problems. So from the point of view of dynamical systems on stationary problems. So that is second order problems with the Laplacian as the leading order term, and then some nonlinearity, or also fourth order terms with the bi-Laplacian as the leading order term and some nonlinearity, all with directly boundary conditions on some domain omega, which has some regularity, which actually finally we will see there is actually no irregularity is needed, and F is some given nonlinearity with some smoothness and growth assumptions and so on. So I will put emphasis on the fact that omega is a very general domain here. Mainly I will be talking about the second order case, simply because the fourth order case is more or less analogous. So the aim is, as always, when we do computer-assisted proofs, is to derive conditions for existence of a solution in some close, which means small, and explicit neighborhood of some approximate solution. So that's, I think that's a common goal in all computer-assisted proof techniques. So the conditions I'm talking about here are either of general type, for example, the smoothness and regularity assumptions on the nonlinearity F, or the regularity on the domain, to be verified analytically, and more special conditions to be verified automatically on the computer, which is a certain set of inequalities which have to be set. So the general concept is transformation. Everybody among us knows this, I guess, transformation to some fixed point equation, computation of an appropriate set, which is mapped into itself by the fixed point operator, and moreover, such that T has certain properties like contractivity or compactness, and then apply some fixed point theorem, Banach's theorem, or Schauder's fixed point theorem, to get an existence of a solution U star in U by the fixed point theorem, and that set U then provides the enclosure of the solution. So that is, I think that's a common approach for all kinds of nonlinear problems in analysis. Well, the abstract formulation here, which I want to consider first, is the following. So we have two Hilbert spaces, X and Y, and a continuous Differential differential mapping from X into Y. And the problem we are looking is the zero finding problem for this nonlinearity F. So now let's first look at this abstract problem and look at how we can get existence and bounds for this problem. So we start with an approximate solution, omega in the space X. So that looks a bit innocent, that omega has to be in X, that actually contains some conditions, as we shall see later in the application. Let's consider L to be the Fréchet derivative of the nonlinear operator at this approximate solution. So that's a linear bounded operator from X into Y. And now, excuse me, we suppose that we have some constants, delta and K, and a non-decreasing function G with the following properties. So suppose that we have computed that. I will talk later in the applications how to do that. So first of all, this delta is a bound for the residual of the of f of omega, so of the approximate solution measured in the norm of the space Y, of course. And so if omega is a good numerical approximation, then that delta should be a small number. Okay. So the next thing is we have to bound the inverse of the linearization of this f prime of omega. We have to bound the inverse of this linearization by this constant k here. And that will be the most challenging part as well analytically and also computer assisted wise. Next is we need some local Lipschitz type bound for the derivative of the nonlinearity of that form here. So we have f prime omega, this is the approximation, plus any u minus f prime of omega measured in the norm of bounded linear operators is less than or equal to this function g, which we assume to have at hand applied to the x norm of u. And we want g to tend to 0 as g tends to 0, as t tends to 0. So let's suppose for the moment that we have these terms, delta, k, and g. So then we need in addition that this operator L, f prime of omega, is also onto. So from this condition here, of course we know that it is 1 to 1, and we need onto in addition because we want to involve the inverse of L in the fixed point problem. So to get this onto, there are again various options to achieve that. If we were only talking about bounded domain problems on bounded domains, then we could use compactness arguments and Fredholm's alternative to achieve that. So then 1 to 1 would imply onto. But since we want to include also unbounded domains, we don't have the desired compactness at hand for that purpose. The compactness usually comes from compact Sobolev embeddings when we apply that to a partial differential equation, but this compactness is not available for unbounded domains. So here I will choose another way for getting that this operator is onto. Namely, we specialize to the case where the Y, the image space of the nonlinear mapping, is the dual space of X, right? So that's the space of all bounded linear functionals on X. And then there's a canonical isometric isomorphism between a Hilbert space and its dual, defined simply by this form, right? And we assume that is an additional assumption I want to make here, that phi inverse L, so that's the mapping from X to X, is a symmetric operator, which means that LU, now we are in X prime, applied to V is the same as LV applied to U. It has to hold for all UV in X. That's the, in applications, that's the usual symmetry assumptions on differential operators. So when we have that, this operator is symmetric, phi inverse L is symmetric, then we know, moreover, it's defined on the whole Hilbert space. And we know, of course, that symmetric operators defined on the whole Hilbert space are self-adjoint. Furthermore, phi inverse L is 1 to 1. This is by assumption, I go back one page, by this assumption here, this is 1 to 1. And that implies that the range is dense. Self-adjoint and injective operators always have dense range. And since phi is an isometric isomorphism, that means also the range of L is dense. Furthermore, we also know that the range is closed. This is again an easy consequence of this assumption here. So the range is dense and closed, so it is the whole space. So that gives this onto-ness of the operator L in this choice for this space one. Okay, then the transformation into a fixed point problem. This is classical, this is Newton. So I go through that quickly. So here is the equation. We can transform it in this way. So that is obviously equivalent. This term cancels with this one. F of omega cancels, and so f of u equals 0 is the equation remaining. And then we introduce the error between the true solution we are looking for and the approximate solution, that is v. And so this line above here is equivalent to f prime of omega or L applied to v is, well, the right-hand side here, and u is replaced by v, omega plus v. All right, and now, since we know by our assumptions and further calculation that this L is 1 to 1 and onto, so it's bijective, so we can invert it from the equation, and then this gives us our fixed point operator, and that gives us our fixed point problem. And now, by our assumptions on these numbers delta, k, and little g, we can control this term by delta, we can control this term by k, we can control this term by little g, and that gives a rise to the following statement. If we put v to be a ball centered at 0 with radius alpha, alpha is still unknown, then we can rather easily calculate that this set v is indeed mapped into itself by the fixed point operator t if this delta is less than or equal to alpha over k minus g of alpha, capital G of alpha, where capital G is the primitive of little g. We call little g is this local Lipschitz bound, k is the bound for the inverse of L, delta is the bound for the residual. So if we look at that condition in this picture here, so the right-hand side, alpha over k minus g of alpha as a function of alpha looks roughly like this. So for small alpha, this g vanishes superlinearly, right? Because g vanishes at 0, so the primitive vanishes superlinearly. So that means for alpha to 0, this is the crucial term. This is a decisive term. So that curve here has slope 1 over k, right? And later for bigger alpha, the nonlinear terms contained in g will pull the curve down below 0. And this condition here requires that this defect bound delta has to be below this dashed line here, which indicates the maximum of this curve. If we then have delta here, then alpha is down there. So that means delta has to be sufficiently small, and that's a very natural condition for a computer-assisted proof, of course, because delta is the residual of the approximate solution. So that's quite clear. Before I continue, maybe a little remark here. So if our nonlinearity in the problem is a polynomial, then also this little g, which is the local Lipschitz bound for the derivative of the nonlinearity, will also be polynomial, and also capital G will be polynomial. So this is a polynomial equation inequality for alpha. And since alpha is the radius of the ball we are enclosing the error in, some people like to call that the radii polynomial approach, right? So because that's polynomial and alpha is the radius. But this is actually nothing but this condition which ensures that the fixed point operator maps E into itself. Right, so that's so I think that's clear. So in addition, we need either T is compact if we want to apply Schauder's fixed point theorem, or we need that T is contractive if we want to apply Banach's fixed point theorem. In this case, of course, we need an additional contraction condition, which actually after some calculation is this here, k times g of alpha is less than 1. And if you think of the fact that hopefully we can get a small alpha out of this other condition, which we just discussed, then since g of alpha tends to 0, as alpha tends to 0, then this term is hopefully also small, and so we have a good chance to satisfy that inequality too. Actually, one can show that under suitable additional conditions, which are natural and satisfied in almost all examples, that this inequality here is the crucial one, and that the contraction property actually is a consequence of that one. So that's the crucial one we have to satisfy. So then there's the theorem, then there exists a solution such that f of u equals 0, together with this error bound by this number alpha, which we just computed from this inequality. Well, now, before I come to the application of all that to partial differential equation, I want to make some remarks here on the more general level, including other people who are doing similar work. So, so far, so this Newton-Kantorowicz type arguments leading to this theorem here are more or less common to all methods providing bounds and existence and bounds for solutions to partial differential equations. And so the differences between the methods occur when we fill this with life, so to say, when we choose the Hilbert spaces X and Y, when we describe the methods how to compute these various terms like delta, K, and maybe also little g, that then difference arises between different methods. For example, the people who do Fourier decomposition, this is actually a majority in this community, I guess. What they do is they take a rectangular domain, and then they take the Fourier decomposition of the equation, so to say, of both sides of the equation, assuming that the basis for the Fourier decomposition also is a basis of eigenfunctions for the leading term operator. And then assuming polynomial nonlinearities guarantees that we can, on the Fourier decomposition basis, can write the nonlinearity as a convolution term. And well, And then we are in a sequence space. So, sorry, I should say, when I talk about Fourier decomposition, I mean Fourier series decomposition, not Fourier transformation decomposition. So Fourier series decomposition. So then we're in a sequence space, and these spaces X and Y and all the operators occurring in this approach are then operators in these sequence spaces. And these sequence spaces are rather convenient, and you can get all these bounds in a nice way in these sequence spaces. But the drawback is that we have to assume that the domain is a simple one, right? So the domain needs to be a rectangle to be able to do this Fourier decomposition. And since I want to avoid, so I want to include general domains, this is not the approach I want to take. Actually, I want to make one remark. So far I said that the Fourier decomposition approach requires rectangular domains. In these cases, certainly we can do this Fourier decomposition. There's one paper I know by Arioli and Koch, where they do that for circular domains, circular disks, right? So here we also have the eigenfunctions of the Laplacian, which are essentially Bessel functions. We have them at hand, but the Bessel functions have an unpleasant property concerning nonlinearities, namely products of Bessel functions cannot be expanded in terms of Bessel functions in an easy way. So the Banach algebra property is missing. They solve that by using a nice polynomials, Zernike polynomials, and with this approach they can transfer the Fourier decomposition approach also to circular domains. But here, as I said, I want to be able to treat rather general domains, and that's why I do not take any Fourier decomposition, but my spaces, X and Y, and all these terms act in function spaces, not in sequence spaces, okay? And actually Sobolev spaces. And now I go back for 3 pages. There are also differences in the methods, of course, computing these terms, is mainly computing this constant K here for the inverse operator. So in the Fourier decomposition community, this K is usually obtained in the following way. First, one calculates an approximate inverse to this operator L and comes the bound for this approximate inverse, which is then can be done usually by numerical linear algebra, and then has to incorporate this error between this approximate inverse and the true inverse, so to say, in order to get that inequality. And this is possible in the sequence spaces. But as I said, that is not possible for general domains. If we go to function spaces, then there's also another approach here by my friend Mitsuhiro Tanaka. He also uses some kind of inverse, of approximate inverse first, namely by projecting this operator L into some finite dimensional subspace, and then computes this inverse for this approximate inverse operator, and then later has to bound the projection error bound. So the error of that projection, which went into this finite dimensional subspace. And this is also possible for many domains, for more than rectangles, for many polygonal domains, for example, but it's not possible for unbounded domains. At least there is no, with some little exception in the one-dimensional case. And so when I want to include unbounded domains, this is also not the method which can be chosen. Okay, so that I think gives enough motivation why I want to do that in a different way. So let's look at problems of that type. So I omit the gradient here, which of course can also be added in this equation, because otherwise this becomes technically a bit too complicated. So we're looking for weak solutions of that problem. Weak solutions, that means multiply by test function and do partial integration, then you get the weak formulation. And here we assume just that omega is a Lipschitz domain. Actually, even this Lipschitz property can be cancelled, as one sees when one looks at it in great detail. So really, omega can be any domain in Rn, any domain, bounded or unbounded. Then we take X, our space X in the abstract stacking is now the space H10 of omega. So weakly differential functions with weak derivative in H1 and vanishing on the boundary. Here's the inner product on this space X, the gradient U in a product plus some parameter sigma, which is positive or at least non-negative, times the L2 product. Well, sigma is certainly has to be positive when the domain is unbounded. Well, okay. So the space Y, as I said, is the dual of the space X, which means the set of space of bounded linear functions on X, which in case of X being H10 is usually abbreviated as H-1. So now the Fréchet differentiability of our nonlinearity F requires some growth conditions of F, which I don't mention here in detail. At least the only thing I want to mention that if n is less than or equal to 2, so if we have an ODE or a two-dimensional PDE, then this still allows exponential growth. So this is still rather general. Okay, so now the first task in the abstract setting is to bound the defect, right? So the residual. So of course, F, the curly F, the calligraphic F is of course this operator here on the left-hand side. And so what we have to, so calligraphic F measured in the Y norm is here this expression measured in the H-1 norm. So to get such a bound, so I think the easiest way is to first do the following. First compute another approximation besides this approximation omega, which is of course an approximation in H10 of omega. First compute a second approximation, which is an H diff of omega, which means that the divergence of that row has to be an L2 function. And that shall be an approximation to gradient U. I'm not saying here how to compute such an approximation, but that can be done. And then if we have that at hand, then we can estimate this residual as follows. So we introduce the term minus divergence rho here and subtract it again. And so then we get by triangle inequality simply this splitting here. And now we use the fact that the H-1 norm of the divergence of any vector field is less than or equal to the L2 norm of that vector field. Okay, so that's a very general inequality. And how to bound this term? Now here we have L2 terms, so that's an L2, and this is also an L2 because rho in is an H diff. So we can bound this term by an embedding constant times the whole expression in the L2 norm. So this is the embedding constant from L2 into H-1, which by duality is the same as the embedding constant from H10 into L2. And this, so that's the Poincaré, if you wish, it's some kind of Poincaré constant, at least if the parameter sigma is 0. Otherwise, if sigma is positive, this is even simpler than Poincaré. So we can easily compute such a constant C hat here. And so now we are back to L2 norms to be bounded. And that, so that means you have to bound integrals. And these integrals can be bounded, well, if F is simple, for example, polynomial, then we have a polynomial expression here, and then we can compute these bounds more or less by hand without error terms by choosing, for example, quadrature formulas which are exact for polynomials of the corresponding degree, and the same here. If F is not polynomial, then we have to use quadrature formulas plus remainder term bounds. Okay? But these are techniques which are, so to say, I'm not saying easy, but they are mathematically easy, but they are technically complicated, right? To compute these remainder term bounds. And then we get bounds for the residual in the desired way. Okay, so the next term, which we have to calculate is a constant k. So here I wrote it again, is a constant k, which bounds the inverse of this linear operator L. So first of all, the linear operator L here has this form minus Laplace plus Cu, where this coefficient C of x is given by the derivative of the nonlinearity evaluated at the approximate solution. So that's this is the operator L, which is curly f prime at omega. Okay? And for that purpose, for calculating this k here, we first use again this canonical isometric isomorphism between a Hilbert space and its dual. Recall y is x prime here. And this canonical isometric isomorphism in this concrete application here reads like just minus Laplace and plus sigma. You can easily calculate that. So then we can also see that phi inverse L is symmetric in the sense I mentioned before, which comes from the fact that this operator L has the symmetric form. And that means we can, first of all, transform our desired inequality in the way that on the right-hand side, we introduce this phi inverse. We call that phi is an isometric isomorphism. Isometric means it pertains to norm. So that means the norm phi inverse Lu in X is the same as Lu in norm Y. So here we have now an inequality Ux less than or equal to K times phi inverse Lu in the norm X. So that is an inequality with norm X on both sides. And phi inverse L is, as we saw earlier, a self-adjoint operator on X. And that means that this K is simply given by 1 over, here's minus 1 over the minimum of the moduli of all eigenvalues where lambda ranges in the spectrum of that operator. And that's the approach I am choosing. Namely, compute this K via eigenvalue bounds, right? That's the crucial thing. So via this formula, so to say. And that is what also works for unbounded domains. And so here the spectrum of this inverse of this operator contains essential spectrum, or can contain essential spectrum. And it does contain essential spectrum, in particular for unbounded domains. And we need to do that analytically and eigenvalue bounds. So let's first talk about this essential spectrum a little bit. So that there is no general strategy to how we can do that in a very general case, but let me talk about some examples of applications, examples where we can do that. For example, first we can replace here omega by 0. So we assuming that omega is defined or is computed on some bounded domain. So even if the true domain is unbounded, one will compute the approximate solution usually on an unbounded, on a bounded subdomain, so to say the computational subdomain. So when we replace this omega, which is non-zero only on a bounded subdomain, by 0, then this coefficient of course changes, and also this operator changes. But the change of that operator when replacing omega by 0 is a relatively compact perturbation of that operator, because only the coefficient changes on a bounded subdomain. And such relatively compact perturbations are known to create the same essential spectrum. That's the famous theorem by Weil. So which means this essential spectrum stays the same when we replace omega by 0. And so what we have to do to compute the essential spectrum of our given operator here is the same as calculating the one where omega is replaced by 0, the essential spectrum. And well, now consider, for example, the case now where when this f or the f of the u at least does not depend explicitly on x. So then replacing omega by 0 means that the c is now a constant. Okay, after this replacement, c is a constant. And that means this is a constant coefficient operator. And well, and for those, now depending on how the domain looks, we can calculate the essential spectrum by Fourier transformation. For example, if this is a strip type domain, we can do that, or if it's a quarter space, or if it's a full space, this is, in these cases, always possible to calculate the essential spectrum of this operator with omega replaced by 0 by Fourier transformation. Other cases where this can depend on x, for example, in a periodic way, then we could use Fouquet theory to calculate essential spectrum. So, okay, so that is essential spectrum, which can usually be done along these lines. And the second part, of course, for calculating this lower bound for the spectrum or the modulus of the spectrum are eigenvalue bounds, right? So it's in addition, which come in addition to the essential spectrum. Now, of course, for eigenvalue bounds, we are no longer allowed to replace omega by 0 because eigenvalues, of course, changed when we change the coefficient. Well, so here is the eigenvalue problem we have to look at. And of course, first thing to do is we multiply by phi to get rid of this inverse operator. And if we do that, we have Lu equals lambda phi u, and we rearrange terms a bit and arrive at this. So here's the sigma, which is the parameter from the inner product. Here it's again. And here is the coefficient of C of x. Now, well, if we replace this 1 over 1 minus lambda by a new spectral parameter, that's one thing we do. And the second is now we fix our sigma to be bigger than C of x for all x and omega. And then recall that's the parameter in the inner product. We can freely choose that. And if we choose it bigger than C of x, then this is a nice positive weight function in this eigenvalue. This is our new spectral parameter. And recall that we are looking for lambda eigenvalues neighboring 0 in order to get a lower bound for the minimum. Here we need the eigenvalues neighboring 0 for the eigenvalues neighboring 1, okay, because that 0 goes into 1 for that new parameter. And recall also that the left-hand side, when we formulate this eigenvalue problem weakly again, so multiply by test function and partially integrate, then on the left-hand side, we just get the inner product in the space X. Okay, here's the inner product in the space X, and here is some bounded bilinear form when just this factor times u times phi integration. And so now I want to talk a little bit how we can get eigenvalue bounds for such kind of problems with an inner product on the left-hand side and a bounded bilinear bounded term on the right-hand side. So eigenvalue bounds. So here's the eigenvalue problem I'm looking at, and this B is here's some bounded Hermitian positive bilinear form. So when we talk about eigenvalue bounds, we can again ask there are again other methods for doing that. So the Plum has created some eigenvalue bounds for special problems, and an interesting method has been developed by Shufeng Liu. He will also be one of our next speakers in the following weeks. I forgot in which one precisely, but not so far ahead. And but all these methods again work only for bounded domains. Right? For example, in Liu's method, he uses a projection and a projection error bound similar to Nakao's approach. And again, that does not work for unbounded domains. So that's why here I propose something else. So that's our problem. And there is a very easy access to getting upper bounds to the eigenvalues, which is as follows. Suppose we have computed approximate eigenfunctions. So these eigenvalue bounds again are now done by computer assistants, of course. I forgot to say that. I should have said it. So suppose we have a computed approximate eigenfunctions, u1 tilde to u capital N tilde in our space X, of course, and they are linearly independent. Then define n by n matrices, which correspond to the left and the right side of the eigenvalue problem, but now only for these finitely many test functions, ui tilde uj tilde in X, and b ui tilde uj tilde on the right. And so, and now suppose that we have computed the eigenvalues of the matrix eigenvalue problem a0x equals lambda a1x. This matrix is a1, and order them by magnitude. And then we can say, if the largest of these, lambda n, is still less than, strictly less than the infimum of the essential spectrum, which I abbreviate by sigma lower bar s, if that is satisfied, then there are at least n eigenvalues of the given problem below this essential infimum of the essential spectrum, and we have the inequalities. Okay, so that gives in an easy way, gives upper eigenvalue. We just have to start with approximate eigenfunctions. That's big scale computation, so to say, for the given problem. And then we are just left with a matrix eigenvalue problem. And that, of course, so if to conclude that we have true upper bounds here, of course, we need verified eigenvalues for this matrix eigenvalue problem. But that can be done by nowadays standard methods of verifying numerical linear algebra. And here we need to check this inequality, essential spectrum, less than infimum of essential spectrum. Of course, we need to know about the essential spectrum. That's what I talked about earlier already. Okay, so suppose that we have successfully computed these n upper bounds, the eigenvalues, then of I go back to get this minimum here. Upper bounds are not sufficient. We also need lower bounds to write. And this is now done as follows. This is more complicated actually than the upper bounds. This is done here by the Temple-Lehmann method. Let us first of all suppose that we have these approximate eigenfunctions and the upper bounds less than the essential spectrum as before from the Rayleigh-Ritz computation. Moreover, we need here a second set of basis functions, namely let me call them W1 to Wn, and these are functions which have to satisfy these inequalities here. So Wiv in the X norm is V to this our right-hand side bilinear form, Ui tilde V for all units. If we have a partial differential equation problem in mind, this is just a boundary value problem. This is a boundary value problem for the Wi with right-hand side Ui tilde, roughly speaking. So it's a boundary value problem. And if we want to have these exactly in our hands, this is, of course, more or less impossible. We can't do that. We can't calculate exact solutions of a boundary value problem. So that is the Lehmann approach, which has this big problem, which is hard to do in practice. But for that, there is, let's go to the last line here, or the last but one line. There is a considerable improvement of that condition by has been given by Görisch about 30, 40 years ago. And that is a bit technical, so I don't talk about this improvement here in detail. But I just want to mention that this problem is more or less solved by Görisch. So this problem is gone, that we have to solve boundary value problems exactly. But there's a second term which is unpleasant. We need some number rho, which is such that the largest Rayleigh-Ritz bound, upper bound, has to be less than rho, and this in turn has to be less than or equal to the next spectral point following after lambda n, so to say, which is an n plus first eigenvalue lambda n plus 1, if such an n plus first eigenvalue below this essential spectrum exists, and it's the infimum of the essential spectrum itself otherwise. And this is, again, a hard problem to calculate such a rho, and this is answered by a Homotopic method, which I will explain on the next transparency. And now, so suppose we have these W's, then we can define a third matrix besides A0 and A1 by this expression. So Wi, Wj in the X norm. And now the rest is easy, or it's numerical linear algebra again. So then consider this matrix eigenvalue problem. And under the assumptions are made, we can easily show that this matrix here on the right-hand side is positive definite, and this matrix on the left-hand side is negative definite. And so that has negative eigenvalues, mu1 to mu(n). Let's order them like this. And here then are the lower bounds for the eigenvalues as desired. So let me mention how to compute that rho. So that's the crucial thing which remains after this problem is solved by the Görisch approach. So this is the problem we need to talk about, how to calculate that rho. And here's the Homotopic method for obtaining such a rho. Here again, I repeat what we need. So that's the highest Rayleigh-Ritz upper bound, and that's the exact next eigenvalue, or the next spectral point, so to say. This is done, so the homotopy involves a family of bilinear forms, Bt, where T ranges between a parameter T0 and T1, and such that, first of all, this bilinear form, for fixed U, if you plug in U, comma U, then this bilinear form is decreasing, okay, it's decreasing. And moreover, for each T, for each parameter value T, the eigenvalue problem with Bt on the right-hand side is, roughly speaking, of the same form as the given problem. Namely, it has at least n plus 1 eigenvalues below its essential spectrum. So this n plus first eigenvalue could actually be dropped here, but make it technically more complicated. Next, at the beginning of the homotopy, we know the eigenvalues, or at least bounds to them. So we know the eigenvalues, and at the end, we arrive at the given eigenvalue problem. So this homotopic family connects an easily accessible eigenvalue problem which we can solve in closed form, or at least bounds to them in closed form, connects that to the given problem. And then there's the following consequences by the first two items here and the min-max principle, Poincaré's min-max principle, we can directly conclude that the kth eigenvalue with parameter value t, of course that depends on t, right? So lambda kt is the kth eigenvalue of the problem with bilinear form et, and that's increasing in t for each fixed k. That's the first thing to note. And in particular, that means that the n plus first eigenvalue, or the n plus first spectral point, so to say, is increasing. And at the end, we arrive at the given problem. So that's lambda n plus 1, the desired eigenvalue. And so we can choose rho to be equal to this expression here, lambda n plus 1 at t0. And we know that by assumption, the eigenvalues in the base problem, so to say, of the homotopy, this can be chosen and we get the lower bound to n plus 1. But we also need the second inequality here. And so that can only be chosen if lambda n is actually less than this known value. But this is not quite pleasant because this last condition, in a sense, requires that there is some interlacing between the eigenvalues. So the nth eigenvalue of the given problem still has to be less than the n plus first of this base problem. And this is unpleasant because that, in a sense, it requires these two problems, the base problem and the given problem, to be, in a sense, sufficiently close. Otherwise, we can't have that interlacing. And that is not desirable because a closed form problem close to the given one is a requirement which we cannot always satisfy. But here is no homotopy yet, as you can see. We only use the beginning and the end of the homotopy. So the intermediate steps are used in order to avoid this unpleasant side condition. Then it is really a general purpose method, which I will explain a bit in the picture. Suppose here is the base problem. So here on this axis here we have the parameter t of the homotopy running. So here we have, let's say, 5 eigenvalues of our base problem, which we know in closed form. Okay, so then we continue along the homotopy. Let's say for homotopy value delta, we compute approximate eigenfunctions and we compute upper bounds to these 4 eigenvalues now, first by the Rayleigh-Ritz method. So that's easy. So now we know that all eigenvalues increase along the homotopy, right, by construction. So in particular, the 5/5 eigenvalue increases. So that means the 5th eigenvalue for this problem at parameter value delta is larger than or equal to this value lambda 5,0. So that means we can choose this as the value rho for our problem at delta because the true 5th eigenvalue is higher. And with this rho, now we can calculate the remaining lower bounds to these 4 eigenvalues, not to the 5th, only to the first 4. And so then we have enclosed these eigenvalues. Of course, now we can continue this process until it's at some parameter value s. Here it may happen that the upper bound computed by Rayleigh-Ritz hits this line here. And then we cannot continue further because when we continue further and this upper bound increases that lambda 5,0, then the argument breaks down. So we stop first for that moment and now continue only with 3 eigenvalues. So we increase the eigenvalue parameter further than we are at that parameter value. And we know that also the 4th eigenvalue further increases. So here we had a lower bound for the eigenvalue at that parameter value. So here we are certainly above this line with the 4th eigenvalue. Again, that means we can choose this value as rho for computing these lower bounds by the Temple-Lehmann-Görisch approach, right? We can continue again until again this here is a hitting of that line and we continue with 2 eigenvalues and then at the end here we arrive with 2 eigenvalue bounds for the first 2 eigenvalues. And this homotopy obviously, as the picture shows, can treat cases where we have no interlacing. So here are the first eigenvalues of the base problem and here's the 3rd, here's the 4th, and here are these 2 are certainly not interlacing with these 2. So the remaining question, how to build this homotopy here, how to choose such a family of bilinear form. I will show you in the examples which I'm talking about now. So there's the first example is the one which has been dealt with together with Joe McKenna from Connecticut and my former research student Moyer. That's a quadratic nonlinearity, and on the right-hand side we have a parameter times the first eigenfunction. So here the domain is the unit square, and that can certainly be also treated by the Fourier decomposition approach. So nevertheless, I want to start with a simple example to show you a few things. So it has been an open problem, or respectively conjecture, since the 1980s. Or the question was, are there at least 4 solutions of that problem for lambda sufficiently large? So 2 solutions can easily be obtained by variational methods, but the question or the conjecture was, are there more? So what we did, we chose the value lambda equal 800, then computed first, computed 4 essentially different approximate solutions by a numerical version of the famous mountain pass theorem. So there is a McKenna together with Choi developed a method for a numerical version of the mountain pass lemma. But of course, that does not give existence, in contrast to the original mountain pass theorem. And essentially different means that none of these 4 solutions is an elementary transform of another one. So, for example, when you have a solution which is not rotation, so you can by rotation you can get formally new solutions, but they are not counted here by reflection. So we improved now these approximations by finite Fourier series. So here Fourier series meant only in the numerical approximation sense. So finite Fourier is cut-off Fourier series and spectral multigrid methods to get high accuracy approximations. And then our accessions and enclosure method proved indeed that we have 4 essentially different solutions. Well, in a sense, 2 years after that result, maybe also inspired by our paper, I think, Dancer and Jan gave an analytical proof also of that fact. So here, one word on the eigenvalue homotopy, which of course is needed here. Here it is quite simple. So when the domain is simple, also the homotopy is simple. Our operator L, which is minus delta plus function C, right? Minus delta U plus C times U, and replace this function C by a lower bound, by a constant lower bound. Then and that's our base problem for the eigenvalue homotopy, right? And so this constant coefficient problem, of course, can be solved in closed form on such a simple domain. And so that requires that we have, that we can solve the base problem in closed form. And now the homotopy, we deform these constant coefficients, which are lower bounds for the coefficient C. We deform that into the true coefficient C of X. And that gives all properties which are needed in the homotopy. So that's quite easy, and this is what I call a coefficient homotopy. Here are some results. Here are the defect bounds delta, these constants K. For the inverse, here are the error bounds, and here are pictures of the 4 solutions. These 2 are in a sense, analytically easy ones. They can be obtained by variational methods. Here are the 2 new ones. This one has a symmetry only with reflection at this axis. This has symmetry only with respect to reflection at the diagonal. All right, so this is So here is the picture of the homotopy for one of them. So it's the second of these 4 solutions. Here are these hitting points, as I explained on the general level. And so here we started with some eigenvalues, and at the end, this closure for this one, and this lower bound for the next one, which is sufficient to calculate our constant K. Here is again a bifurcation picture, which I will not. So here's seems to be a bifurcation of 2 branches, which gives us these interesting 2 additional solutions, which are these 2 here in the level set plot. But this bifurcation picture is not verified yet. Next example is the Gelfand problem. So there's minus delta U equals delta exponential U. So I'm not talking here about the problem on omega 0 squared, because that is solved analytically. And it is known that there is this bifurcation picture like this. This is this nose-shaped bifurcation, and this branch then goes up to infinity when the very lambda goes back to 0. So that's well known. So what we did actually in joint work with Christian Wieners, we took a more interesting domain, which is is a symmetric domain, which has re-entrant corners, obviously. And here, first of all, at the first attempt, we obtained a boring picture of this in the same way, which was similar to the problem on the unit square. So no new solutions apparently. But then we changed the domain a bit. We cut off a little part here. So this side is a bit shorter than this one. And then starting the Newton algorithm again, here's a third dimension in the bifurcation picture to get a better distinction of branches. So then starting the Newton iteration and numerical branch following, we observed that there were substantial unsymmetries were developed in that solution. So what we did then, at that point, for example, we reflected that solution about this axis here, and then rearranged the boundary values a little bit because we call that the domain is unsymmetric, but by rearrangement, of course, we can make it can satisfy the boundary condition again. And then started up with this reflected solution, started the Newton iteration again. And then fortunately it converged to an approximation on a new branch, right? And now, on this new branch, then we applied our computer-assisted proof technique, and again could then prove the existence of that new branch. So also here, one word on the eigenvalue homotopy. So here the problem is not just cannot just be done by taking a coefficient homotopy, but we need something more, because here for that domain we even don't know the eigenvalues for the Laplacian because the domain is complicated. Here we used another kind of homotopy, which I call domain deformation homotopy. You choose a rectangle which surrounds this omega. Okay, so and on that rectangle, again, of course, we can solve now just with the Laplace operator, no coefficient c. We can solve the eigenvalue problem for the Laplace operator in closed form, and then deform that rectangle into this domain geometrically. And now, since this, and deform that in a monotonic way, so that the domain is shrinking. And with this shrinking technique, it can easily be proved that eigenvalues increase again. So we have the structure of the homotopy. And this is actually much less complicated than it sounds. There were only 2 steps in this deformation homotopy, which to arrive at the given problem. And then a second homotopy starts, which is the domain which concerns the coefficients again. So then after we have the eigenvalues of the Laplacian, then we can start a second homotopy to bring in the parameter, the function c of x, as in the previous example. Okay, another example was this one with Pacella and Rütters, this Emden's equation, let me understand delta u equals u to the p. On some domain, and we're looking just for positive solutions, so that means equivalently by the maximum principle that's equivalent, we can write it as problem with a modulus to the power p. And so we are interested here in particular in this domain, which has 2 infinite legs, so it's an unbounded domain, which in addition has this corner here. And we are interested in proving the existence of a symmetric solution, symmetric with respect to reflection at this diagonal axis here, so to say, with one bump centered at the corner. Okay, and so maybe I skipped this computational part for the computation of the approximate solution. That is technical. So for the computation of our constant k, for the inverse operator, we again, as indicated on the general in the general description, bound for the essential spectrum and for isolated eigenvalues. So for the essential spectrum, we consider again some compact perturbation of our operator. So we replace the coefficient c of x, which is appearing here, by this coefficient, characteristic function of omega 1, where omega 1 is just the left upper corner of our domain omega, so to say, times pi squared over pi squared plus 1. This is for technical reasons. This is an optimal coefficient density. And then we can show that the essential spectrum of this operator, so of the given operator and this new operator with this 0 coincide by what I said before, so the relatively compact perturbation. And then for that operator here, or this operator, we can estimate the boundary Rayleigh quotient do Rayleigh quotient estimates to obtain that the essential spectrum or the whole spectrum of this operator is contained in this interval, which means that in particular its essential spectrum is contained in that interval, but the essential spectrum of that coincides with the essential spectrum of the given one. So here we have our bound for the essential spectrum, which is needed. And for the isolated eigenvalues, now here I repeated the same calculation, so I don't repeat it again. For our eigenvalue problem, phi inverse L u equals lambda u, this is what we arrive at the end. You may remember that here, that in weak formulation, that gives the inner product in H10, where the constant sigma is the coefficient. This parameter sigma is chosen equal to 1 here, and this is our bilinear form little b, which I indicated on the general level. And so now again, we use our eigenvalue bounding technique to compute the bounds here. And well, so I should also lose a word here in order, no, wait, so I should also lose a word here, how to do the homotopy for the eigenvalue computation. I go back to the picture of the domain now, it's this one here. And so you see, again, of course, we do not know the spectrum of the Laplace operator in closed form on this domain. And we also cannot use the approach via an enclosing rectangle because the domain is unbounded. And if the rectangle, if we take the whole right lower quarter of R2, so to say, then we get bounds which are useless. So what we did here, actually, we replaced the coefficient C of x by a piecewise constant lower bound. So we make some cuts here with, and then to get a step function only with respect to x, so it's constant in the y direction. And so get a step function as a lower bound for the coefficient, analogously on this side. And then the crucial point is the following. We cut the domain here and here. We make two cuts here. So we get three subdomains, which is this little square and these two strip domains. And now we solve three independent eigenvalue problems on this little rectangle, on this strip, with Neumann boundary conditions at these interfaces. Neumann boundary conditions. And we can solve all these three eigenvalues in closed form because simply by separation of variables. And now the crucial thing is that if we take the union of all eigenvalues for all these three problems, take the union of all their eigenvalues, and then order these by magnitude, then the Poincaré min-maximal principle tells us that we get lower bounds to the eigenvalues of the true problem, index-wise lower bounds eigenvalues of the true problem with these step function coefficient by this union of the eigenvalue of the three problems here. So this is by Poincaré's min-max principle. And now so going back from this base problem to the true problem, which is this one here, we have to remove these cuts, so to say, and this is done by penalty terms so here line integrals are introduced in the bilinear form, which line integrals over the jump of the function, so to say, and then driving the parameter in front of this penalty term to infinity, then enforces at the end of the homotopy that we get the eigenvalues of the true problem. And then in a second step, we use coefficient homotopy again. So from this piecewise constant coefficient, we go up to the true constant in the coefficient homotopy as before. And this is actually the homotopy picture for this coefficient part, which is actually the most crucial part. Yeah, and here we have the delta. Here we have a bound for our k. The sim indicates which involves symmetry, which improves that constant a little bit. Here are additional constants which are needed for the verification, and then arrived at this so existence of a solution which with this error bound. Okay, so maybe so I have another example. This is this traveling wave problem on the whole of R. But since my time is already over, I skipped this last example. So thank you very much. So yeah, maybe because if you give me one more minute, since I have skipped this example, now I also skipped my last page with this advertisement for our book, which we wrote. This is actually together with Nakao and Watanabe. So Nakao I mentioned earlier, and this book has appeared about half a year ago. And it is written in 3 parts. The first part, Nakao and Watanabe describe their method. In the second part, I describe my method. And in the third part, we also give a very short overview about the Fourier decomposition approach. And well, I hope you find it interesting. So thank you very much.
Thank you very much, Michael. I'll vouch for the book. The book is fantastic.
Thank you.
People haven't seen it.
So maybe I should leave it here so that you can copy the Springer link.
Yeah, it is also, by the way, a reference on our website.
Oh yeah, yes, I forgot to mention that. Yes, thank you, JP, for doing that. So there is so
Sure.
It's mentioned on the webpage. Yes.
So there's still plenty of people around if people have questions for Michael.
Maybe I have one. Hi, Michael.
Yes, please. Hello, Maxime.
So yeah, maybe a bit technical, but since I'm currently trying to use those techniques, I thought maybe it's a good time to ask. So when you introduced for the first example, you had the parameter sigma for the scalar product.
Yeah.
Which was, okay, you could see because of the 0th order term, the C that, okay, taking sigma large enough made sense because then you have something which was positive and it,
Yes.
understand why it helps. So now assume you have additionally a 1st order term in the equation.
Yes.
Is the sigma still helpful or does it not make, I mean, taking a large sigma, does it have, in practice, does it make anything different or not really? Or
Yeah, so when you have a 1st order term contained in the nonlinearity, then it makes things very different. So the main reason is not just this parameter sigma. The main reason is that now our operator L, so the linearization at the approximate solution is no longer symmetric.
yes.
And recall that here many arguments here depended on that operator L, or better to say phi inverse L being symmetric. Sure. So we have to find a new approach for that. That is essentially as follows. So the constant K, which you see here. So suppose now that L is not symmetric. So then this constant K can nevertheless be obtained by, roughly speaking, computing eigenvalue bounds to L star L. Okay, L star L. And the true answer is not L star L, but phi inverse L, the whole thing star, phi inverse L. So that's the operator we need to consider when L is not symmetric, or phi inverse L is not symmetric. But when you formulate this L star L problem weakly, then we get, so to say, a bilinear form on the left-hand side. There is phi inverse L, comma phi inverse L with the 2 arguments. And on the right-hand side, we have the L2 product in X. And now for this problem with phi inverse L, comma phi inverse L, that can be treated again by eigenvalue bounds as before. And the parameter sigma, which you asked for, plays a role here, but not as simple as it does here, because this is not the eigenvalue problem we get in the case where L is not symmetric. We get a more complicated eigenvalue problem.
Yes, but still, so I mean, adding the sigma helps in practice, you mean, even for the 4th order problem then?
Yes, also for the 4th order problem. So sometimes it's needed, sometimes it's not needed. So for example, for the Gelfand problem, this coefficient C is anyway negative. Mm-hmm. And that means we don't need sigma. Similar also for other problems. But when sigma has positive parts, then we need sigma. Otherwise, we have an indefinite weight function here. Of course, we can also try to calculate eigenvalue bounds with indefinite weight functions, but this is certainly more unpleasant than just choosing the parameter to make it definite, right? To make that
I see.
But you are quite right. So if there are first derivatives, then things get more complicated. But still tractable by the same methods.
Yeah.
Of course, the book contains details on that.
Other questions?
I have a question. This is Evelyn.
Hi, Evelyn.
Evelyn, hello.
So the question I have is about the Gelfand problem, where you talked about how there was this whole new set of solutions in the case where you had asymmetries. And I was wondering if you've explored at all how this forms as you're moving from the symmetric to the asymmetric case, or rather from the asymmetric case into the symmetric case, how these bifurcations look.
Ah, yes. So, okay, yes, thank you for this question. So actually, what happens if we, so to say, remove this symmetry, this asymmetry or this asymmetry and go back to that case, then this branch approaches this one. Yeah, right. You can see my cursor, right?
Yes.
Yes.
Yes. And so that, and then there seems to be a bifurcation point here. So that seems these two branches bifurcate. So please, you have to see that in a three-dimensional thing. So that is, roughly speaking, this branch is now in the bifurcation picture in a vertical plane, and this branch is in a horizontal plane, roughly speaking. And so this peak then this seems to move over here, but we were not able, but maybe for accuracy reasons, I'm not quite sure, to prove that bifurcation point. So here one could extend actually this example by trying to prove that here's a bifurcation point. And of course, you are an expert, Evelyn, for being able to do that. we didn't try too hard, right? Because our main emphasis was proving a new branch. But we might be able to prove bifurcation, but we were not successful with doing that yet.
Thank you.
Yeah.
Well, if there aren't other questions, I'd suggest we thank Michael one more time and for a wonderful talk this morning.
Pleasure.